where we are. So we're looking at this three manifold with a contact form and then an almost complex structure. So here we're assuming the conformal Laplacian is positive, and then the fourth order Chinese operator is now negative. And then from here we have the positive mass theorem. So now we know that the Green's function with a pole at a point P has this expansion 1 over 2 pi rho squared plus a constant and then smooth part where omega is smooth and it's vanishing. Okay, so this is in the CR normal coordinates. Based on P. So we want to make use of this function to help us construct the test function in order to compute the so-called quotient. So Q of U is the integration of LU times U divided by L4 norm of U squared. So the goal is to construct a test function U so that Q of U is strictly smaller than, say, on the standard sphere, Q of S3 of, say, the function 1. Okay? You remember last time I showed you that if for some test function this is strictly smaller than that, then the minimizing sequence for this functional will converge. Okay? Hence, minimum of Q of U is attained. Okay. Oh yeah, I should have mentioned this. So when you say the Yamabe problem, usually people mean the solution of the Yamabe problem is generally a critical point of this function. Then in that sense, this problem had already been solved. I forget her names. Gamara.
Two R's and there's no H.
Huh?
Gamara. Student of us.
Yeah, and then there's another guy.
I forget. Lady.
Okay.
This is
the
lady.
lady. And she showed that the subtle points, well, critical point exists.
High Morse index.
Yeah, but doesn't know what the index. So in that sense, she solved this problem. But as you see tomorrow, we really want to have the minimizer. And when you have the minimizer, you actually have a much stronger state. So anyway, she showed a long time ago, maybe year 2000, critical point exists. And this is using Barry's notion of critical points at infinity. So it's really a Morse theory in function space. And to show that there must be a critical point. So that's actually a remarkable kind of argument. But anyway, return to our story. So how are we going to construct this test function? Well, the idea is the following. So just going to draw this picture. So this line represents the CR normal coordinates with origin at the point P. Okay? And then the CR normal coordinates exist only up to a radius, say, rho 0. which we will assume to be very small. If it's much bigger, we just take a small rho 0. Then what we're going to do is that put down in the CR normal coordinates the standard bubble. Okay, so standard bubble. And this I already wrote down last time. Is use of lambda depending on x plus iy comma t is lambda over lambda to the fourth power t squared plus 1 plus lambda squared on t squared. Square, and then square root the whole thing. Okay? So this is a one-parameter family of test functions. When lambda gets very large, it gets very, very concentrated near the origin. So what we want to do is, say, go out to radius 2 rho 0, and after that, we want to attach the Green's function. So this is going to be the Green's function. This is use of lambda. This is the Green's function based at this point. So in here is a gluing region. So I'm going to write down the formula now. Okay, so I wrote down the Green's function with this error term omega. Okay, so we're going to let u to be equal to u sub lambda. Okay, when rho is smaller than rho 0, that is, in here, we just use that bubble, standard bubble. And then in the gluing region, we write it this way. We take a constant epsilon naught times 2 pi, and then take the Green's function, and then minus, oh, I have to take a cutoff, so psi is a cutoff. So it's equal to 1 in row first and row 0, and equal to 0 when rho is greater than 2 row 0, and in between, just it's like linear. So cutoff function times omega zt, and then plus psi times 1 over lambda. P. Okay. And write down what phi is in a moment, but this is for the region rho is between rho 0 and 2 row 0. Okay. Finally, on the outside, I take epsilon 0, 2 pi Green's function. Okay, so what is this phi? Well, phi is the difference. So phi of ct is just t squared plus minus z to the fourth plus 2 over lambda squared minus z squared plus 1 over lambda squared minus 1/2 minus rho. Okay? So this is basically rescaling of this function by the factor of lambda squared.
Can you expand a little bit this choice of A large or not?
Well, it's very simple, right? I want my test function bubble here to capture this part when lambda is large, epsilon 0 is small, and then there's going to be a relationship between epsilon 0 and lambda so that these two guys actually glue up. Okay? So this is the gluing region. Let's just write it carefully this way.
So this choice of fees to make the point match with
Yeah.
or not.
Yeah. So now the important thing here is that if you choose epsilon 0 to be equal to 1 over lambda times 1 plus 2 pi, this mass, and then rho 0 squared, okay? Then u is piecewise. See what continues. Okay, so now I will just outline the computation. Okay, to really compute this full expression will probably take more than an hour. So we just outline how you manage to do this computation. So we have to recall certain things now. The CR normal coordinates. So recall now, in the CR normal coordinates, the contact form looks like 1 plus rho to the 4th, theta naught. And then there's some error term outside of theta naught, so we'll have rho to the 5, C, and then the contact. And theta 1 is square root of 2, 1 plus rho to the 4th. C, that's the main part. And then there's error term, rho to the 4th, DC bar, and then perhaps a little bit of theta naught. So what is this? Rho cube, theta naught. Theta naught is the standard contact form of the Heisenberg. Discussion the CR normal coordinates. Okay. And you write down, therefore, from here you see that theta wedge d theta is of order 1 plus rho for theta naught. And the vector field dual for theta upper 1 is 1 plus rho for natural Z1 vector field in the Heisenberg. Okay? And then you have some error. And then perhaps a little bit of component in T. You go Q. So the main term, subradian of U squared, is by definition 2 times the product of Z1 differentiating U times Z1 bar differentiating. Okay? So from this setup, now you can go ahead and compute. Look at the so-called quotient. Okay? So first, notice that because of this error of the volume form, you go to the 4th. You can easily see that this is called the denominator. Okay, so volume is really the same. Volume, the standard contact form of the sphere, plus little o of 1 over lambda squared. Okay? That's a simple calculation. Okay? So we don't pay attention to the denominator. Okay? Now we compare the numerator. So compare energy term. U on this manifold with that of the standard sphere. Okay. So the main term is going to be this energy expression inside smaller region, rho less than rho 0. Okay. So let me write down the contribution.
So, sorry, Paul, but here you mean, when you mean volume, you mean the L4 norm of your test function, right?
Yeah.
That's
volume is u to the 4th.
Oh,
times.
okay.
Sorry.
It's not the theta wedge d theta. You're not doing saying that.
Here is a volume naught.
Yeah, but he means the L4 norm. He does not mean the contact form norm or the contact form.
All right. So first term, so subradian is d theta, rho less than rho 0. So this is essentially, so we're going to split the subradian into the standard part that is using only this piece without using the remainder. Okay. So that's given by standard subgradient in Heisenberg with the same function squared. Okay, theta naught, which is theta naught. Okay, so there's some error here, here, and here, but we just keep this part. Okay. Rho plus rho 0, and then after about 10 minutes, you see that error is below 1 over what is it, rho 0 squared. The second part of the energy now, yeah, is the gradient squared plus RU squared. So we look at RU squared. So RU squared, theta was d theta in the same region. So this is also, now you can replace this RU squared with theta naught, which is theta naught plus error. 0 and plus below integration. Basically, rho to the 6th error and then u squared theta. Okay. Rho that's rho 0. Okay. Because that high vanishing order, basically you can ignore the error, but we need to understand what this is. So this thing turns out we're going to just estimate it by absolute value. This whole thing will turn out to be error term. Okay. So the absolute value of RU squared theta naught, where is d theta? So the absolute value is going to be the following. So here I make some observation that shows you how the computation is done. Remember, in the CR normal coordinates, R is scalar curvature at the origin is 0. And in fact, it vanishes to actually third order. R at the origin is 0. R gradient is 0. Sum of the plus B of R at the origin is also 0. And R differentiating in the 0 direction. You see the 3 vector field direction is also 0. So this means that the Taylor series expansion of R looks like 1/2 xx x squared plus 2 xy xy plus r y squared. Okay. Plus rho q. So when you do this, you're using this equation. This means that when you integrate this quantity here on the sphere of radius rho, this thing cancels out, so you don't see this term fighting that term. But the sum of Laplacian is all xx plus 1. No contribution. So this is the part that you need to see that explanation. Okay? To see that this is at most of order constant rho to the 4th. U squared C naught. Rho that's rho 0. And now you plug in the shape of U to see that this is equal to constant rho 0. So the same as the reading times. Okay. So this term is going to be viewed as error term. And then now you have to worry about the remainder part. That is when you start gluing these functions here using this formula. Okay. So the main part I want to extract is I want to say, okay, let's just look at this part. That's the main contribution. That's coming in to bring me down a little bit from the standard sphere. The remainder part is going to contribute to error. All right. So now this is quite a long computation. So I just write down some of the terms. Okay. Oh, sorry, I'm not quite finished. I only did this, right? So I have to make use of the equation that U satisfies in the Heisenberg. We need to integrate by part, sorry. So continuing on line y, so 3, the main term is going to be changed. Yeah, so subgradient d0 of u squared sigma naught is d sigma naught. Okay. Now I have converted everything to the Heisenberg, so I can put my part in the Heisenberg. Okay. Rho as 0. So I'm going to use the equation u satisfied. So this is going to be u to the 4th sigma naught with sigma naught, right? And then there's a boundary term. So plus minus 2 times integration the sphere of radius rho 0. Okay? And then I have lambda to the 4th on z squared plus lambda squared to the 4th. Then I have 4th t squared plus 1 plus dp dt, where I write the vector z, which is x plus iy, as exponential id times modulus z. Okay. So you do this. We're going to do this integration later. Okay. All right. So that's the leading term, and now we have to look at the remaining part. So I need to compute the main contribution from here. So number 4, really got many terms here. So let me just write it out. Okay? So integration over the complement of rho less than rho 0. So I'm looking at subgradient u squared plus r over 4. So as I said, I want to pick out the main contributions from here. View that as one region. So this is going to be epsilon squared, 2 pi squared, integration n minus the set of subgradient g squared plus 1/4 squared. And then the remaining guys have split into really four cross terms. And they're really quite small because a lot of them involve cutoff, error, and things like that. So, so basically, all these terms, the error term, they contribute to no more than little order. Okay, so the main term to deal with is this Green's function term. But remember now, the Green's function satisfies an equation, so we have to do integration by part. And so eventually we want to do that integration by part and compare with this boundary term. Okay. So I'm continuing writing this line. Continuing writing this line. So this is equal to so I'm looking at the epsilon 0 squared, 2 pi squared. And then because it is the Green's function, so when you integrate by part, L of the Green's function is 0 now outside the single point. So there's no interior term, so everything comes out to be a boundary. And this is something like S rho 0, 1 over rho squared plus A plus W times 2 over L squared plus B. PV was the angle was before. Okay? So you compute this, and this turns out to be minus 8 pi, minus 16 pi squared A over. Okay. So now you see that this is, even though it's order 1 over n squared, but it's got a fixed constant A. Now if I shrink my radius,
So where did the lambda come from in that term? I don't see a lambda in the integral.
epsilon,
Oh, epsilon naught has a lambda.
So you have a fixed choice of this or not.
no, I'm going to move. I'm going to move rho 0 smaller and smaller. That's what this little O means. Yeah. You fix rho 0 smaller and smaller because A is fixed. The mass of that point is fixed. So we move rho 0.
Epsilon naught contains a lambda.
Yeah. Oh, sorry, you erased that. Epsilon naught.
You didn't say it.
Well, where is
No, I
it?
just
So
erased
not.
it. Epsilon naught is equal to 1 over lambda 1 plus 2 pi A. Right?
So the other thing that I don't see is the minus. The minus. Where did you pick the minus? That's crucial.
Yeah. Of course, that's crucial.
That's
I want it to be
that's the
minus,
main
right?
point.
Yeah.
So where is the minus coming from that integral?
You have only computed Green's function term, and there is the energy gradient in term.
That's almost the sphere constant.
In the fourth term, now, the energy gradient BA.
Yeah.
Here,
U is, I'm picking out the main point of U. I'm calling it this function plus some error here, right? So the main term is what I'm picking out. So when you integrate by part, this is LG times G, right? Yep. Now, to answer Sahun's question,
that's what I mean, you have term 1 there, which this is the error.
yeah, I just want the error term to carry. So where did it come from? So it must
That
be
is just the sphere constant. So this is the one that's the key, the minus sign. I know the energy is lower than that. But done.
So this one when you do integration by part, you have a minus.
Yeah, because this minus and that one push the value of the cellular constant down from the sphere.
Yeah.
That is the one for the sphere.
Oh, it's integration by part, right?
Yeah,
So this is
There is a
this
minus
G,
sign.
EGDM, so there's a
Yeah,
minus.
minus,
Okay. All right, so that explains how important this guy is. Because it's fixed quantity, the rest you can scale to make it smaller than this new contribution. So that's how you show this is strictly small. Okay. And that's sufficiently large. Okay. All right. So this gives the existence of minimizer. Now I want to make some comments. So now we have shown that the three-dimensional CR Yamadi problem has a minimizing solution. And the whole thing depends on the positivity of mass, depending on this number A being strictly positive. Okay? So now I want to give you an example to show that it is really necessary. Okay? So, example of CR structures where L is positive, the mass term A is positive mass, no longer hold.
So you're saying that you need the non-negativity of the finite in some sense.
Yeah.
It is really there.
Okay. So where does this come from? Well, surprisingly, it comes from a very small perturbation of the standard contact structure on this 3 sphere. Okay. So we're going to deform S3, standard S3, standard complex standard. Once you deform J, so take one family of deformations of J. So when you deform here, remember to do the mass, you have to correct it so the scalar curvature becomes positive. So it's u sub S squared. Okay. So we try to look for such a deformation. So deformation EPS JS is given by, let's call it a tensor.
So sorry, if I take just the Rossi example, it doesn't work
We don't know quite sure.
because that would be the natural candidate.
We know it doesn't embed, so we
Yeah,
know
it
something.
doesn't embed, and it's
So we
the
know
finite
something
is
is wrong.
negative. The finite is negative for that, right? For the Rossi example, it has to be. So Webster is positive.
Yeah, time is negative. How do you know the mass is negative?
Yeah, but my question is that why it would be a natural candidate.
Yeah, of course.
So you don't know. This is what
we
you're
don't
saying.
We don't know. As you can see, this type of computation is very time consuming. We get very tired. But anyway, here's how you do it. Okay. So when we do this, let's think about E11 is given by the following type of function. It's actually a holomorphic function. 1 over, oh sorry, not the S3 Heisenberg. Which one? So T plus I mod Z squared plus 1 to the power K. It's just need to take K large. So why do you need to take K large? Because if K is a small integer, we're not quite sure it decays at infinity fast enough for all the computation to hold. But we are sure that if say K is greater than or equal to 3, all the computations will be okay. So now you compute the second derivative with respect to S of the mass, J, C. So it turns out it looks like minus 3 over 4 integration R double dot theta with theta, the background, the Heisenberg contact form, and then minus 3 over 2 R dot U dot theta. This formula for general deformation. But then an explicit calculation will show that R dot is actually point-wise equal to 0. So at the S equals 0. This is so the main term is R double. So you compute this R double dot. So one computation, R double dot turns out to be minus 2 E11 1 R squared minus 2 E11 E 1 bar derivative in the 1 derivative, then minus 2 the conjugate dot E11 1 So now when you integrate this quantity, because all these derivatives, you can do integration by part. Okay? So the integration part, total dot, is going to give you minus 2 integration. So here, when I compute this, I've already assumed this is holomorphic. This is holomorphic. Therefore, E and that's simplified this computation. Well, so that's clear now, right? Second derivative of mass is negative. So it goes down. We know the first derivative is 0. We know that so in this deformation, the mass actually goes down. So in fact, this calculation really says if you do any holomorphic direction, you change J in J dot to the holomorphic function, then you always decrease. Lots of holomorphic functions. So this tells us the mass is largely negative.
So in this doing this, you can keep L in positive along bodies.
This is small deformation.
So
L is a robust quantity, so small deformation will not change the possibility.
So you said the E11 is defined over the high school, right?
Huh?
E11 is defined well. In
Yeah,
last
it's on the high school.
the parameters are three or what?
On the whole Heisenberg.
More high school.
So this is an example where the mass is negative, right? So what's really not answered in this argument is that when the mass is negative, maybe you can still minimize, right? Minimizing sequence may still converge. So that's where my co-authors and I disagree. I think when the mass is negative, A is negative, then when you go back to the original 3 manifold, the minimizing sequence would actually all blow up when you hit the standard sphere value. In other words, the value of this Q of U will be always greater than the standard sphere. Q is 1 standard sphere. So this, if you take a minimizing sequence, this is the height of the Q1 standard sphere. So you start out here, and then when you minimize, the infinite is actually this value. We know that by simply concentrating. Okay? So you can get as close to this one as you want, but we want to say that all minimizing sequence must hit this point, and they must all concentrate. So there's no meaning. I think that's the picture. It's a good analysis problem, and I think
So
if you're hungry, go ahead and
in
do
your example,
you
so
might want
M3,
to do this computation.
suppose your M3 is embeddable. Your M3,
What's
your example is M3 embeddable.
M3 is the Heisenberg.
But you change the complex structure, right?
Now I change the complex structure.
Yeah. Is that still embeddable?
Is it still embeddable?
No, but your
I'm not so sure, right?
First of all, it's non-compact.
Yeah.
It's non-compact example.
yeah, but it's okay.
I think most likely it's not, but I have no proof.
So, but do you have like a compact example for this phenomenon? A really compact example?
Oh, this means that if you take this deformation, they would actually correspond to you're deforming CR structure, right? So you're actually deforming the CR structure on the standard sphere. Then the masses are up. Even though this computation is for Heisenberg, it is really an example of extreme.
Anyway, when you quoted this student of Bali, that result also uses P positive.
Pardon?
No,
Result
No?
there was no P.
There was no P.
No, the result of Gamara, there is no Panais.
Well, this is a completely different argument. This is Sabas argument.
Yeah, but
Here's a fantastic argument that says,
any
if
information.
you look at the function space at infinity. So if you do these more theory, look at the energy function and talk about critical point at infinity, and there's a big topological argument that says there must be critical points. It's a very good existence theorem, but for geometric purpose, it's in some sense useless because we don't know what it is. We don't know the energy level. For all we know, the energy level could be 10 million, where it should be about 1. Okay. So now I want to go back to the first result that made all of this really possible. So this is called an embedding problem. So I'm given a 3-dimensional CR structure, and I'm assuming, well, general question is, given such a 3-dimensional CR structure, is it the boundary? Of a 4 real dimensional complex manifold. Now, because we assume this is strictly pseudo-convex here, so we won't have strictly pseudo-convex. So this is actually part of the for the last part of the question that's answered in higher dimensions completely about 30 years ago. So when n is greater than or equal, when n is greater than 1, that means n is dimension at least 5, and then you assume j is integral. Remember now what that means, that once you introduce the almost complex structure, the subdifferential decomposes into round p b equals round p bar p, right? And then integrability means that p bar p squared. So this condition now is meaningful in higher dimensions, and under this condition here, such a thing is always there. This is the result of the set in the in fact, his argument is more general. It also would apply to 3 dimension if you know something else. So N3 theta j is embeddable if this box B operator is closed range. Okay, remember box B here is something like minus sub quasi plus 9 times t, the read vector t. So this is the result of cone. Okay, the idea here is very simple. What you do is that you start out with a smooth differential embedding into pi dimension R real space, because you can think about real space as complex space. Will have the dimension, and then you try to correct the embedding by changing the embedding function into holomorphicals. But in order to do that, to be able to solve for holomorphic function, you need to be able to invert this operator. That's when you need the closed range. Okay. So what we do, follow. So this is a theorem with going here. And then Chu in Taiwan and myself. We say that this operator, if now control of us is positive, and the fourth order operator is non-negative, then any non-zero eigenvalue of box B. In other words, suppose I have eigenfunctions of box B u plus is equal to n of u equal, then it's different from 0, then we have an absolute lower bound for n. So remember now, if the whole Laplace is positive, then you might as well assume the scalar curve is bounded away from 0, positive from 0. Okay, and then this assumption, then we know that this lambda here is strictly bigger than the e. But if you think about this operator, this sub-elliptic operator, okay? So if you have the non-zero eigenvalue bound away from 0, then it gets close range. Okay? Therefore, you better make several remarks about this. Okay. First, I want to rewrite the Penny's object. So we're going to define P3 of phi to be phi 1 bar 1 bar 1, then plus I portion A1 1. And then the upper one. So when you do upper and lower, you're raising the lower indices using the metric on the contact direction. Okay? The same Riemannian notation. So P3, phi is a scalar function. This is going to be a 1 form. Okay? And then P4 of phi really is going to be a scalar. It's going to be a divergence of this one. So it's just this thing here. Okay? And take one. This is the P4 operator. But you can rewrite it knowing that box B looks like this. You can rewrite it this way. You can rewrite it as 1/4 box B bar minus 4i 1. Also write that as 1/4 box B bar box B and then plus 4i. Okay, there are different ways to write this operator. So now you see the connection with box B. So that's why the Penny's operator is important. It allows you to solve box B. And now I can easily explain now this P greater than or equal to 0 condition will automatically follow if the torsion is 0. And the reason is the following, right? This P4 operator, when the torsion is 0, then these terms go away. That means box B commute with box C bar. So they can be simultaneously diagonalized. So box B and box B bar can be simultaneously. Right. Okay. So the eigenvalue of P is certainly not there. If you don't use this argument, it's actually very difficult to see that. If torsion is 0, it's very difficult to see that P4 is where you go 0. The reason is the following. The way I write it out now doesn't make much sense. Okay? So, but if you write it in real, this is a real operator, so I can rewrite this as sub Laplace squared plus T squared, and then plus all over terms. Then you see what's going on now, right? Because this is a positive operator, this is a negative operator. Okay? In the kernel of, because this guy is the divergence of this one, so kernel of P3 is what we call the Dewey harmonic functions. This definition was first found by Eric Beck for the 3 dimensions. Of course, he didn't make any use of it. But if you take the divergence of this one, you pick up P4. So the kernel of P3, the P4 contains the kernel of P3. So it contains Fourier harmonic functions. If you're the boundary of a complex manifold, there's a lot of Fourier harmonic functions. So the kernel is infinite dimension. Okay? So this condition, P is greater than or equal to 0, it's really a non-trivial condition because you're saying, look at the leading terms. They're really trying to cancel each other. And somehow everything combined to conspire so that it's non-negative. It's a highly non-trivial condition. And that's why we say this is really an infinite number of conditions. Okay. So after all this talk, let me show you the proof. And once you see the proof, you can understand why some people are very upset. Because the proof is just 2 lines. Yeah, proof of this here. When I say 2 lines, it's really 2 lines of argument, but maybe a couple hours of computation. It's a Faulkner formula. Okay. So, first of all, I know the following. I have minus 1/2 bar speed of d bar b of any function squared. So if you're a differential geometry, you've done this type of computation many, many times. But in the case of CR structure, it's quite complicated. It really takes a good understanding to know how to organize it into the terms you want. Okay? So it turns out it looks like this. U 1 bar 1 bar, U 1 bar, and then U 1 bar 1, U 1 bar, and then minus 1/2 B bar B U. The metric inner product with B bar B plus B, and then minus B bar B plus B U, and then minus T3 U bar U plus R times. Okay? That's P3.
Just P3 and then you conjugate.
Conjugate. P3 is not a real operator. It's a conjugate. Okay, so now assume U is eigenfunction of box B. And now we integrate. Integrate. So integrate here. All these terms. Okay. And because this is divergence, this is 0. So you get the nice identity. Okay. So you do some integration by parts here. The important thing here is that here you can do the easy integration by part, but the main observation you use is that u1 dot 1, u1 dot bar, one order integration plus p u squared. So it's 2. Okay, so that tells you how to handle this term. Okay. And then the rest, that's a purely positive term, just leave it alone. So you get, after you put in 0 here, you get lambda times d dot p u squared integral is equal to integration u dot 1 bar u this absolute value squared. And then plus now the integral part here, with this one over here, you get p4. Okay. So p4 integration, and then plus r p bar. Okay. So now the assumption of positivity here says this term is a negative constraint. Okay. Pull it out. It's greater than infinite R times. So because now you're assuming it's a non-zero eigenvalue, so d bar d of u is non-zero, cancel the stuff. So then just figure infinity. Okay. So this is a simple, natural, sort of intrinsic proof of embeddability CR structure. Why do I say that? Because the positivity of these two operators with CR invariant conditions. Zero. CR. Okay. So now I want to sort of try to answer the last question, right? So this condition is very nice. So when is it satisfied? Big question. When is this condition? Oh. Okay. Well, of course, you can tag on this extra condition that makes it embeddable. So it's going to be boundary of a complex two-dimensional variety. I should have. Yeah. So Cohn's result here, if say if box B is closed range, then you can CR embed this three-dimensional manifold into high complex dimensional space. So you have going into Cn, where the component functions of Cn restrict to holomorphic functions of N. Now, a lot of previous work.
Sorry, could you repeat Cohn's result?
Hmm?
What is Cohn's result? Could you repeat? You said Cohn's result.
Joe-Cohn's embedding theorem,
Embedding.
the closed range if and only if.
It's closed range, so you can embed into Cn holomorphic functions. And then the work of Harvey and Dawson.
So actually, put them well prove if you have homomorphic splitting function. It's always embedded. Homomorphic split. And the Conley treaty, it did not prove embedded. He said, under that condition, there is a homomorphic splitting function.
Yeah.
So it's a combination of a lot of people's work.
But let me just point out, if the non-zero eigenvalue is bound away from 0, then of course the inversion of box B is easy. The inverse of box B is upper box. So you can basically do anything you want.
So, just one tiny comment. I just want to point out that there is a certain similarity between these theorems and the old result of Lich-Nerowitz for the Laplace operator, which has the same flavor. It's bounded below by Ricci also. The Laplace.
Yeah, of course. I mean,
It's the same thing.
after our formula, many people just jump in. So they prove the sharp inequality and so on and so on. Okay. We are very happy. We have no argument with that. Okay. But Harvey-Lawson here says such an M is the boundary of a complex analytic right. This is a boundary without singularity at the boundary. But this is a two-dimensional complex right. And then the singular set are isolated. So such things are understood. So in fact, say X has smooth resolution. Therefore, N is actually the boundary of a complex manifold.
So what condition?
Hmm?
What's the condition? Always.
Two dimension, isolated singularity can always resolve.
No, that's okay.
Yeah.
Harvey-Lawson.
Harvey-Lawson has a general statement which applies to a very general situation, but when this is three-dimensional CR structure in CN, it always bounds a complex. Complex.
It's like
It's
plateau
three
problem.
dimensions, okay?
They are doing a plateau problem. Complex plateau.
Okay. So it's a boundary of two-dimensional complex manifold. So our guess is that it should be always true. If it's the boundary of a complex two-dimensional manifold, the T operator should be non-negative.
So you believe in the domain, domain of a bunch of domain is always okay.
Let me see. So that's the next thing I'm going to say is the thing. So if now M is the boundary of omega, is a domain C2. So now that domain has to be strictly pseudo-convex. We still don't know whether Penny's operator is non-negative.
So what if you assume it's strongly convex? It doesn't help.
The difficulties are the same.
I thought you were trying to convince me you did something.
Yeah, the difficulties are the same. But for small deformations, it's true. For general, I don't know.
So allow me to finish, right? So we have a sort of beginning of a theorem in this direction. So this is again subroom, submiddle, Q, so we say that if we can deform small deformations of boundary omega, this is C2, where this starting guy here has no portion. Okay? Right? It has no portion, then the Penny's operator is always not big. So we put the small deformations Penny's operator. Preserves the zero condition. Preserves this condition P4 is non-negative.
If something has no portion, then P is always positive.
Yep.
So you are saying
If you deform starting from 1, which is no torsion, then small deformation, preserve the solution. P is not negative, we are not saying torsion is 0.
I don't understand.
I say if the starting guy P is non-zero, small deformation P is still non-zero.
No, without torsion. That's what
Beginning guy without.
Because there are a lot of zero eigenvalue, 94 into negative one.
Yeah.
Actually, it's
Yeah,
impossible.
it may become positive ones and become negative.
Okay, so all of this sort of meshes well with what is known previously. Okay, so the oh yeah. First, we'll talk about the Rossi example. This is really Andreatti problem. But Rossi studied carefully. So we look at standard S3, C canonical, J canonical. Now we do a small perturbation. So now we deform J by, say, J sub T is equal to, well, but once you have J, you can figure out what is Z1, huh? The whole multi-dimensional length 1 is just like convex. So Z1T is said to be Z1 plus T times Z1. Putting a constant multiple of Z1, T small. Then, what's known is that for JT, all CR functions, remember we are on F3, right? So it's a remarkable thing. For small deformation, all CR functions are even functions.
So
That is
original T equal to
U
0,
of
is
X
that
is
even
equal to U of minus X.
But on the original S3, you don't have linear functions.
Yeah, so this is for T getting to 0. Once you move away from the standard one, you lose half of your holomorphic functions. Right? They're all even. But even functions cannot separate points. Therefore, it cannot embed at all. Right? So we make some comments about this. But on the other hand, these are even functions. They're holomorphic functions. So we view them as functions on the real projected 3 space. How do they embed? Not in C2, but in C3. You can write it down explicitly. So that's a very interesting thing going on. And for this reason, I pose the following question. That is, if you take a 3-dimensional CR structure,
Is the Rossi's example only for 3?
yeah. Everything is very special this week. See, this example really comes from Grauer. Grauer studied isolated singularity of complex surface.
So that one is a matter of being 4. B2 to B3, it's probably better. It's with me back.
Yeah. So geometry called it Veronese embedding.
Yeah.
So now, if pi 1 of n3 is finite, but not 0, I think it's not embeddable in C2. It's a very good problem for enterprising graduate students. It's a simple problem. Okay. So one question, okay?
Point 5 has that to do with this, the Rossi example.
Because we like to understand, right? Studying Rossi example gives some of us hint that maybe this is true. See this one here, Rossi example is the best one among these. It doesn't even fit. So if you're worse than that, you should not. Okay, that's my philosophy.
Lot of symmetries.
Huh?
We have a lot of the best symmetries.
the best
are
one
there,
doesn't
and
expect how do
that
you
doesn't
expect the
invent- then
bad
things
actually
with
fit.
worse symmetries
Okay.
should not enter.
Okay. Now let me give you some examples which does embed. Okay. Oh, I should also mention what other people know. So this problem area has been really investigated a lot by Burns, Daniel Burns, Charlie Epstein, Lemper, and then last one is Blank. So in fact, the last work combined the understanding of previous guys. We understood all deformations of S3.
So Paul, the conclusion, the CL function, even is that due to Burns, or the Burns are due to Rossi? So the result is that
That's not due to Russell. It's due to Burns. Small deformations of standard S3, canonical. Okay? So we're going to do it the same way as Ross, but then we're going to put in the variable function. Okay? Look at the type of functions for which small deformations embed. You ask, for which function is possible to embed?
so phi is the function in T, right?
Phi is function on the sphere.
Also,
So you write phi into spherical harmonics, BPQ. Okay? So BPQ is a spherical harmonic. S3. So these are polynomials in Z1, Z1 bar, Z2, and Z2 bar. So P is the Z degree, Q is the Z bar. Degree P is Z, Q is Z bar. So you write P as a linear combination spherical. And their statement is that suppose it's a finite sum. Then they know that this is embeddable. Embeddable small t, provided the following is true. I didn't write it down. You remember?
Yes, I can try, but P bigger than 2 plus 4 or something. You can check for the Rossi example, see what they say is right. But you have to do the rest.
Something like that. Right? Yeah. So it's a very precise answer.
For the Rossi
So
example,
embeddable means embeddable in C2.
No,
yes,
yes.
secant N.
So when P and Q are both 0, that's Rossi, right?
Yeah. So it's okay. So it's a rather complete answer. And you can easily check that for these guys, the penny, well, I say easily check. You can check. If you do a single monomial like that, you can check that the pennies operate non-negative provided distribution sets. So fits very well with our result.
So for this example, this condition already implied P is possible.
For monomials.
Monomials.
Not for general. The monomials.
Okay.
And that's exactly in this range, P is less than P.
Huh?
It only happen P4 is positive only in this range.
Yeah. This is really about 10 years of work. These four guys.
So Epson wrote a lot of paper on this, right?
Yes.
Yeah. Yes. I still remember he keep talking about this every day.
You remember many things.
Okay, so now let me continue talking about this. Okay, that's the first question. It is I1's finite. Right? That's because we work on this. I keep looking for examples of nice, strictly pseudo-convex free manifolds sitting in C2. I don't see any that's finite I1.
So on the other hand, your question is if M is embeddable and simply connected, then you said it should be put in C2? Yeah, surface. I think probably you're right, actually. It's a
Use the Poincare.
for quantum conjecture plus multiple field, I think probably it's okay.
Sphere.
You can get a simple proof with a pointer.
Yeah, you have to go to this time
Almost there.
I will talk about that.
Yeah, he says that. He's trying to say something like that.
Okay, so now what about infinite pi 1? So here's an easy example, right? I simply take a simple closed curve in C2, and then take a tubular negative. When the ball is small enough, it gives you a strict pseudo-convexity at every point. Okay? So S1 cross S2 can be embedded. Zero. This is more interesting one. Mod Z1 squared plus mod Z2 squared plus 1 over mod Z2 squared. It's 10. Okay, so we work on this one more time. Okay, so how do you see this one? Well, notice that this is always bigger than or equal to 2, right? And it's equal to 2 precisely when
Pi is always, this is already in S3. Pi is always bigger than P. That's,
A plus 1 over A is always bigger than 2.
okay, that's Z2, not Z2. Okay, I'm sorry.
Yep. Okay, so Z1 is less than 8. Right? So the Z1 is square root of 8. At each point, in the Z2 direction, you have an annulus. This annulus thickness becomes 0 when you hit the boundary. So you can see the boundary here as belonging to two pieces. One is a circle vibration over this. The other one is the other circle vibration with this. But at the boundary, you glue the disc together. That's a two-sphere. So this is that's nice way to put S1 process. So there are lots of questions people can ask about this embedding question, and most of them are not answered. And I think now, because I think now we have a number of tools that now available, so it's possible to begin to deal with these questions. So, pricing Yang you want to work on hard problem. These are very nice problems, and it really requires new ideas, right? It's not something that 100 people studied before. Not so many. I think in this world there may be 30 of us who think about such questions, right? And we're all very old.
These guys don't work on that list. They all stop work.
So I think this is a good area to get into seriously. Okay, so now I'm over? Stop.
Go on.
No, that's fine.